So hydrogen, which is 1 electron, all right? And remember, when you're looking at the periodic table and you're trying to write the electronic configuration, it's the atomic number, okay, not the mass, obviously, okay? And the atomic number is also equal to the number of electrons in there. Technically, it's the protons, but and we will write the electronic configuration of ions also, like the cations and anions. But right now, we'll focus on the neutral atoms. So 1 electron. There are 3 rules for filling out electrons. Okay, and if you saw the PowerPoint, all right, or the lecture, you saw the 3 rules. I don't remember them as such as to which one is which. I just know what they are. Okay, and so the first one, or one of them, is that you fill the lower energy first. Okay, that was, I think, Aufbau's principle. Okay, so you fill the lower energy first, and that's why I went through the energy with you last time. Okay, so shell number 1 is lowest energy, 2, 3, 4. Higher energy. In the spdf, S is the lowest energy, P is higher, D is higher, and so on, okay? There are some exceptions, but otherwise, that's how you start. So for example, when you're filling for hydrogen, you will start in the first shell, okay? So never from the second shell. Start from first shell, fill in the first orbital in there, which is the s orbital. The first shell doesn't even have P, it only has S in it, okay? And then you have 1 electron in there, okay? That's how you would fill it out. If you were to fill out for helium, 2 electrons, now you still have the first shell, you still have the s orbital, and now you have 2 electrons in there. The maximum number of electrons S can have is 2. Okay, so which means that when we start to fill out lithium, I'll have the first shell, because I still got to start with the first shell, S, okay, my orbital, the first orbital. Now I have to fill 3 electrons, so 2 can go in the first shell, and then I start with my second shell. The first orbital I will fill in the second shell is going to be S. The second shell has 2 numbers possible in it, right? L is equal to 0 and L is equal to 1. That's S and P. Okay, so I will start with S, not with P, and I fill 1 electron there. Okay, that is essentially what you do. All right, and today we're going to go through some of these things really fast. But I want to show you some patterns before I do that. So after lithium, let me go ahead and take sodium. And sodium is 11. And again, I'll start with the first shell, S electrons, and I have to fill 11 electrons now. So I'll start with the 2 here, and then I go on to the second shell, and I fill in my S orbital. Now I'll fill my P, because the next orbital here is P, so 2P. You have to write the 2 again. Don't skimp on that, okay? Make sure you write everything out. So, and by the way, just leave a little room here or in front, okay? Because I'm going to do the box configuration as well. So 2s2, 2P, 6, and I have 11 electrons. Just take a quick count, okay, of what you have on the top. That will tell you that you filled out 10 electrons. Okay, so which means that you still have 1 more electron to fill. So now I go to the third shell, first orbital, 1 electron, and I'm all set now. Okay, it's as simple as that. Yes, Anna?
I don't know if you're going to get to it, so I'm waiting.
Okay, so wait. All right, very good point. These things that we write, these are called electronic configuration, and more specifically SPDF notations. Okay, so when we say that give me an SPDF notation, this is how you're supposed to write out, okay, in there. The other one that that you have to learn how to fill is, of course, the box configuration, okay? And the one that you have right here, this is the one you have, this is essentially box configuration, that you draw boxes, okay? And depending on which textbook you pick up, there might be a box or there might be a circle, okay? And it doesn't really matter. So let's look at hydrogen over here. So when you're filling out the box configuration for this, you have 1 box, which is for S, and you have 1 electron in there, okay? And the 1 electron, how do you draw that electron out? And this is just, I'm telling because this is the first time you may be doing this. In your worksheet, I have drawn this arrow only because Word doesn't have half an arrow in there. Okay, Word has only a full arrow, and a full arrow is also representative of 1 electron. Okay, no problems. But a lot of times you may also see half an arrow. I learned it half arrow, so I usually drew half arrows. Okay, in there, but that also indicates 1 electron. So whether you draw a full-headed arrow or half-headed arrow, it doesn't really matter. Okay, it's your personal choice, whatever makes you feel comfortable. Now we get to the other two laws. The first law is the Aufbau principle, in which you fill from lower shell to higher shell. The other two rules that we have, one is Hund's principle and the other one is Pauli's exclusion principle. Okay, and one of them states that when you fill 2 electrons in a box, they should be in opposite spin. Okay, which is perfect because that is the magnetic spin number. Okay, plus half and minus half. So when we are filling out for lithium, this is how you fill it out in opposite spins, and you will see that in my in your handout also. Okay, that everything is in opposite spin unless I am spinning your mind. Okay, which means that I'm asking you to correct something. Okay, in which case it will be wrong. But otherwise, this is how it would be, and then the 2s would be 1 electron. Okay, over here. So then for this one, the box configuration would be the 2 electrons. Now P, remember, can have 6 electrons, right? And P has 3 numbers, plus 1, 0, minus 1, Px, Py, Pz. So it has 3 numbers, so which means that I'm supposed to draw 3 boxes for this. Okay, and the third rule, okay, the first rule, lower energy first. Second rule, opposite spin. The third rule is that you fill electrons singly first in each of the boxes, okay? And then you pair them up. Okay, that's the third rule. You can start your filling anywhere you want, because remember, these are equal in energy. This is what is called degenerate. Okay, so they're all equal in energy. You can start anywhere. The only rule is that you fill them singly first, and then you start pairing them up. And I have 6 electrons, so that's perfect. It will all pair up anyway. This is more true when there are not enough electrons in P. So when you have 3 electrons or 4 electrons, then you will have to work on that. Okay, and we'll do some examples of those as well. And then finally, my 3s1 is like this. So here's the deal. Okay, this is what I feel about SPDF notation and box configuration, is that you cannot write the box configuration without the SPDF notation. Okay, because only when you write the SPDF notation, only then you know how many electrons to fill out and how to fill them out. So always write your SPDF notation first, okay, and then do the box configuration. That will help you, because if I were to erase all of this over here, then we kind of get lost as to what these electrons are. Okay, so it's much better to have the notation there, SPDF notation, and then write the boxes. Good so far? All right, let me go ahead and write this back again, because I need to show something. 2p6 and then 3s1. Okay. This is all group 1 elements, right? Hydrogen, lithium, sodium, and then potassium, rubidium, those are all group number 1, okay? What I want you to see, the pattern over here is for S1, S1, S1. Do you see that? They're all ending in S1, okay? S1 meaning that you're starting with the first orbital, okay? So whether it is the first shell, second shell, or third shell, it doesn't matter, but you're still filling out the s orbital and only 1 electron in that s orbital. Are we good? Yes? Do you see that pattern? Okay, that's an important part. And then we go ahead and write maybe a couple for the second group as well. So beryllium and magnesium. And don't wait for me. If you're good in this, then go ahead and just write your own. Don't wait. 1s2, 2s3. You don't have to write the box configuration if you don't want to. Just write the SPDF notation. So here's for beryllium and magnesium, and if you look at the pattern over here, you will see that it is all ending in S2. Good? So now, let me take you to the periodic table, okay, and I'll show you some of the things here that are really critical in understanding your periodic table, and then trying to do these configurations in such a manner that life will be a breeze. Okay, and this configuration should be like this then, okay, for you. All right, so first of all, we have the hydrogen and the helium. And do you see these numbers over here, which I'm going to get erased at some point, okay? These are shell numbers, okay, that go down. So this is shell number 1, this is shell number 2, shell number 3, 4, 5, okay? You cannot get to 5 without filling the 4 first. Okay, over here. That's how it goes. Okay, there are some exceptions. If you understand the periodic table with me today, you will have no problems. Okay, in doing the SPDF notation. So, you know, just ask me anything that you missed. So these are shell numbers over here as you go horizontally. Okay, so which means that we have 1, 2, 3, 4, 5, 6, 7 shells. Okay, only. We don't have an 8th shell. We don't need one. It's not that it's not there. There's no need. Okay, at this point for that shell. As you go towards the right hand side, okay, this is how the electrons are being filled in that shell. So in the first shell, if you remember, the first shell was 2 electrons. There, so n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. So 2 here, how many was it? 8 here? 8, 18. 32, okay, and so on. So n is equal to 1. The first shell can have only 2 electrons in it. So that's 1 electron and second electron, and we're done with that shell. Okay? The second shell can have up to 8 electrons. So that is 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay? So that's how you fill the electrons out. Good? Now, a little bit more specificity about here with the periodic table is group number 1 and group number 2. This is going to be always S1. This is always going to be S2. Okay? If you have your periodic tables, this is a good thing to write out, okay, on the periodic table. And if you don't have one, there should be a nice periodic table in the book also with all of this information. But of course, it's always best to write in your own handwriting. Okay, so, and I think I have that in the PowerPoint as well. You can never find things on time. Okay, page 309. Okay, if you have your textbooks with you. So group number 1, always going to be S1 because that's always going to be the first electron that you fill out in a new shell. Okay, the second one always going to be S2. Okay, and those are the patterns I've shown you on the board. All right, that's how it's always ending in S1, always ending in S2. This group here, these two over here, these are known as the S block. Okay, these two over here, because all of these are always going to end in the S electrons. Okay, so this is S block. Right here, where you have 1, 2, 3, 4, 5, 6, these are the P block. Okay, because in the P block, you can have up to 6 electrons in the P subshell. So this is the P block, and guess what this one is then? The D block, and then right down here is the F block. Okay, in the F block, you should have up to 14 electrons, right? Okay, so this is 14, starting from cerium right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, the D block is 10 electrons. Okay, so there are 10 columns for the D block. Are we good? So now you can see a periodic table makes a lot more sense, okay, than it did before, because initially we were just classifying it as metals, non-metals. But now you can see from quantum chemistry point of view, this periodic table just takes a whole new look, okay, to it. It's just completely different. So S block, P block, D block, and then F block. Okay, so now this group over here, group number 3, what will it end in? So group number 1 ends in S1. So group number 3 should end in P1. P2, P3, P4, P5, P6. Okay, so you can write that on the top if you want to. Okay, for yourself, that's how it's going to end. All right, now let's try another thing over here. Let's say I ask you that we're talking about phosphorus. So what is the last electron that you fill out, okay, for phosphorus? So you look at phosphorus, you say it's over here, okay, The last electron to be filled out is going to be in 1, 2, 3, the third shell, and 1, 2, 3. It's going to be a p3 electron. Good? p3 electron or 3p3 electron. Okay, more specifically. Are we good? Okay, so that's how you can pinpoint and say, okay, this is exactly the shell number you're filling in. This is exactly where it's going. Okay, the shell number is going to become a little confusing. Okay, because there's something I have to change here for you, but otherwise, at least the electrons are specific in their suborbitals. Okay, so this is p1, p2, p3, p4, p5, and then p6. So far, so good. Okay, let me just go over carbon and nitrogen over here. Okay, a little bit. So C6 and C7, and this, not C7, N7. And this is just to specify how to fill electrons out when you get to the P. Okay, because I mentioned here how to do that for the box configuration, but still, just to give you an example. So carbon is 1s2, 2s2, and then 2p. And you can just look at the periodic table, and it should be ending in P2. Okay, make your life easy for yourself. Okay, so you don't have to keep counting electrons all the time. You can just look at the periodic table. To fill this out in box configuration, this is what you would do. So 1s2, 2s2, not a problem. But then you will go ahead and draw out the p orbitals. And please always draw it out, okay, completely, like the box, okay? So it has 3 boxes in the P, so draw the 3 out. Do not draw it like this. This is not a good way for drawing out the P, okay? You need to put them together like this so that you know that they're connected, okay? They're part of one orbital. Now you have only 2 electrons in this, and this is what I was trying to say, that you fill them out singly first, okay, before pairing. So then this is how it goes. Okay, that's the correct way. This would be the wrong way of filling it out. Can you fill out this way? No.
No.
Yes, you can. You can, sure, why not? Remember, these 3 orbitals are exactly the same. Okay, so you can fill out the first one, second one, third one, whichever one. The thing is that they should be single. That's it. Okay, that's the important part. You can fill it this way, or the third combination would be this, and they're all fine. Yes, Malik.
Doesn't matter which way the arrows are like.
No, not even that. So, for example, I'm sorry to cut you off like that, but anyhow, yes, you can do it like this also, if you want to. Yeah. So just make sure that you don't do it this way. This is not good. Okay? Yeah. They should be going in the same direction, in the same spin, but singly first. Okay? All right. Those are all the important criteria as you're filling these things out. Okay? And again, you can afford to do this and this kind of a filling only because these orbitals are degenerate. Okay, they have equal in energy, so it doesn't matter which ones you fill out first, okay? But logically, this is the best way, right? This looks nice and neat and all that. So, stick to this. That will keep you, give you a good track of how you're filling your electrons out. Okay, and then nitrogen is going to be the same thing then. So 1s2, 2s2, 2p3, yeah. And then 2 electrons here, 2 electrons here, and then 1, 2, 3. Okay, so singly fill out the electrons. This part becomes really critical in bonding, okay, which is why we need to do this, okay, otherwise I wouldn't be specifying this. Okay, so let me look at your worksheet now, and for those of you who had a little issue with question number 1, pair the following electronic configuration with the same properties. Now, we learned back in chapter 2 that when you have groups, those group elements have the same properties, right? So all you're looking for in these elements then is how they are ending, okay? Because that's how you will figure out whether they have the same properties or not, because they will belong to the same group. So for example, A is ending in 3s2, right? Specifically s2. So you're looking for any other element that is ending in s2, and it is D, right? 1s2 and 2s2. So those are the 2 elements that will have the same properties, which means they belong to the same group. Okay, that's what this question is about. Yeah.
You didn't answer my question, so I'm gonna ask it. Why do you put 3D, why do you put 4S before you put 3D?
So I'm getting there. I'm not coming there.
Never mind.
Yeah. Okay. So I still have to go over exceptions. All right. So then question number 3 is the electronic configurations that you figured out. Question number 4 was not an issue, right? No. Okay. Very good. So then let's go on to number 5. Without looking at the periodic table, write the SPDF notation. That should not be a problem because then all you're doing is taking the electrons and just filling them out. Okay. And so let me get to 18, okay, which is argon. So argon 18, and by the way, when you do your electronic configurations, my advice is to sit with your periodic table, okay? It's the easiest way to do it because all you have to do is go line by line by line and just fill out all the electrons from there, okay? But otherwise, 1s2, 2s2, 3s2, no, I forgot my P, yes. So 2p6, 3s2, and then 3p6, 10, 18. Okay, 18 electrons. Looking at our shells, in shell number 1, I have only s electrons. Shell number 2, I have s and p. Shell number 3, I have s, p, and D. Shell number 4, I have S, P, D, F. Shell number 5, I would still have the S, P, D, F, but remember we've gone only up to 4 of these numbers, okay, or these alphabets. We haven't needed a 5th one yet. When we fill out for potassium, which is 19, you can see that we're starting with a new shell, right? So technically what happened here, what we just did is 18 electrons. So we filled out the 2 over here. We filled out the 8 in the second shell. Are you with me? Yes? And then the 3s2 and the 3p6. The 3s2 and the 3p6. We filled that out as well. But then when we start with potassium, it seems like we are in 4s1, right? That's what it says. So which means that what we did is we skipped this one and we went straight to the next shell over. Okay, that's what we did. So this kind of a thing is an exception to the rule where you say that you fill everything down here first. The energy rule that we have, the Aufbau principle, that you fill from the lowest energy first, it's still the rule. It is still the rule. The only thing is that the 4s orbitals are lower in energy, okay, than the 3d. That's what happens, okay? Now you do that only when you get here. Until the previous chapter, you know, that's what you learned, but then when you get to this chapter, suddenly you start having exceptions, okay? And so there is a little diagram, okay, somewhere which shows you how this thing works, okay? And that is on page 306. If you have your textbooks, if you have the PowerPoint, I gave it in there too. But trust me, you don't need it, okay? You will need the periodic table. Once you have the periodic table, everything is just fantastic, okay? But this is the chart I'm talking about, okay? And this is how you fill electrons out. So starting from 1s, you just keep following the arrow. That's it, okay? So in the beginning, if you need this chart, that's fine, okay? So which means that you fill in the 1s first, then the 2s, then the 2p, and then the 3s, and then the 3p, and then the 4s, which means the D did not even come into picture yet, okay? So it's, you go out first, you fill the S, okay? But then look what happened after calcium. You came to scandium, right, which is 21, and this is the D block, okay? Which means what happens? You come back in here, you fill the D, and then what happens? You go out again, okay? So after D, you are out in P again. Do you see that? Okay, so this is the kind of zigzag thing that keeps happening after the third shell, okay? But if you follow the periodic table, you will not go wrong, okay? If you do this without the periodic table, you may miss that little fact. But if you follow the periodic table, you'll be fine, okay? All right, so we did argon there. Let me do potassium. Actually, let me do calcium, okay? Then we'll get into the transition metals. So calcium is 20. So 1s2, 2s2, 2p6, 3s2, and then 3p6, and then 4s2. So again, if you want to give yourself a reminder, 3D is missing over here. Okay, because we haven't started filling 3D yet. Because 4s2 is lower in energy, okay, than 3D. So then we get to SC, which is 21. One S2, 2s2, 2p6, 3s2, 3p6, 4s2, that is still there, that hasn't gone anywhere, and now you have 3D1. So now you went inside to fill the 3D, which means that you need to make a note on your periodic table that this is 3D. Okay, this is not 4D. So even though this is coming after the fourth shell, or this is in the same row as the fourth shell, this is actually 3D. Okay, so right here, little bit 3D, 4D, 5D, 6D. So it's like one number behind, okay, for everything. So in the fourth row, the D is what we call is sunk in or something like that. Okay, so that's how you fill out for transition metals. Then let me not go sequentially, let me pick some specific ones that we need to work on. And let me take chromium. Chromium is 24. Actually, it's not even, yeah, chromium is the exception there again then. So 1s2, 2s2, and this is where you start getting bored. You're like, I'm so done with 1s2, okay, at this point. So that's when you start using the noble gas configuration, okay? And so then you can say, okay, I'm gonna start with argon. So here, I have argon, which takes care of 18 electrons. Always write the number of electrons here, so you know how many electrons have been taken care of. How many electrons remaining? 6 electrons remaining to be filled out, right? Right, okay. All right, so if you have 6 electrons remaining, and I have argon here, argon was 18 back there, so now I have to start with potassium, which is then 4s2, and after 4s2 I go into 3D, right? Okay, so 3D, and now chromium, all you have to do is just count, okay? So this is 1, 2, 3, 4, so that's 3D4. But this is also wrong. I'm very sorry. This is the second exception, okay, that you will encounter. So the first exception was the energy rule, where the 3D is higher in energy than 4s2. Okay, that's one exception. The second exception comes when you have 3D4, and this is only for D and F orbitals. Okay, it's not for P orbitals or S orbitals. S is of course definitely nothing, okay, because there are only 2 electrons. But not for P, only for D and F. Okay, and this is what happens. Instead of this, it's actually 4s1, 3d5. Why does that happen? We have to write the box configuration for this, okay, in order to see this completely. So 4s2, and for D, you'll have to have a box of 5. And then 4, 1, 2, 3, 4 electrons for the top one. And in the bottom, this is what you have. 4s1 and 3d5. The bottom configuration, where you have all the orbitals singly filled, is a lot more stable than the one on the top. Okay? So you have an exception here also then, all right, is that you have to fill electrons singly out for everything. And this again, as I said, happens only in D and only for F, okay, not for P. You don't want to do that for P orbitals. Okay, so chromium has this, which means that molybdenum may also have this, which means that tungsten may also have a W, okay? It may have the same issue. The other issue will come when you get to copper, okay, and copper is 29. And again, we can start with argon, as in argon 18. So then 4s2, and then 3d9. Technically speaking, that's what you would fill out, okay? Because you have the 4s2 and then 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons for copper, okay? But that's not what happens then, okay? Again, what happens is that 1 electron from S goes into the D, so it becomes 4s1 and 3d10. This is correct and that is wrong. Yes?
Should you do that for every D? So should it always be, so for strontium, it should be 4s1, 3d2? Or is that just from chromium on?
No, not just even from chromium on, just for the chromium group.
Okay.
Just for this. Because by the time you reach to manganese, manganese is 1, 2, 3, 4, 5. It's already singly filled. So it's
Okay.
already stable. Okay? But that happens only in the chromium. It does not happen for
And in
rhodium.
the copper group.
And then in the copper group again.
So just in group 6 and 11 in the
In
transition.
this. Or you can just write on your periodic table to remind you. This is the chromium and the copper. Yeah.
So it's just those two groups are unstable
Yeah,
if
I
it's
know.
not completely.
I just
If
don't
it's
use
not
that
completely
for
filled.
study.
Okay.
So when D is filled out like this with 5 electrons, it's a lot more stable. Or completely paired up, it's a lot more stable as well. Okay? So manganese already is 5 electrons, so it doesn't need to pull any more electrons from S. So it's all fine. Okay? No problems here for manganese. But by the time you get to iron, cobalt, nickel and all that, then there's just too many electrons that it's no reason to pull anything until you get to copper, which is then just 1 electron short, okay, of being completely filled up, right? The one thing that you can have a sigh of relief is that I hardly ever have you do the F electrons, okay? Because F electrons go really cuckoo, okay? And let me show you how they go cuckoo. Okay, so here we had 4, right? This was 4s2. This is 3D. This is 5s2 or 5s, and this is 4D. This is 6s, and this is 5D, right? This is where the F starts. What number is this? What's the shell number for the F over here? 4. It should be 4, which means really after the 6th shell is when you go all the way inside to 4th shell to fill out the F electrons. Okay? Yes? I know, it gets really, it gets more complicated when you get to the F then, okay? Because then you go to inside to fill out the 4F, you come out to fill out the 5D, then you go out to fill out the 6P, start a new shell, go inside to fill the 5F, come out to fill the 760, whatever. Okay, so it gets a little bit more complicated as you go higher and higher. Okay, yeah.
Doesn't that contradict the rule of you're supposed to fill out the lower ones first?
But it is the lower energy. It's not the lower number of shell, it's the
just
lower energy.
So F
right.
has a lower energy than D.
Yes. That's what happens. And that's what happened here also, with the exception, that's why we're filling the D after 4s, because the D is higher in energy than 4s over here. Okay? Yeah, that's the only reason. Otherwise, it would be so much nicer if it was also straight, right? Yeah, but that doesn't happen. Are we good? Now these exceptions, I can't remind you those every time, so please just make a note of it, okay, somewhere. And of course, you can be sure that I will have that on the exam somewhere, right? Because it's an exception, so I gotta put it there and test your memory and see if it works. So anyhow, what I want to do now, okay, for the next 2 minutes, if possible, is just pick random elements from the periodic table and just write out the configuration, okay, and see if that works. And that's how I advise you to do it. By the way, you can watch TV and do this, okay? You don't really have to lock yourself in a room, okay, to do this. So just take your periodic table, close your eyes, try not to go too much down here, okay? So close your eyes and pick an element and say, okay, I'm gonna write out 4, not this. I'm gonna go up a little bit, okay? And take arsenic, how's that? Arsenic good? 33, okay? So we're gonna fill out 33 electrons in under 30 seconds. Are you with me? Yeah, we can do this, we can do this. All right, if you want to write this, you're most welcome to. Otherwise, just stay with me and I'll give you 30 seconds later, okay, to write it out. So 33 is where we are going, okay? All right. So starting from the top, 1s2, 2s2. Yeah, go ahead, say it with me, please. 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p3. That's it, we're done. That was even like less than 30 seconds. Okay, that's how you do configuration. So I really promote the periodic table. Okay, that if you have that in front of you, it becomes a lot easier. You want to do antimony? Yeah, 51? Sure. Under 10 seconds? Okay, 51. Keep our goal in mind. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Come out, so come to 4. Okay, so 1, 2, 3, 4, 4p6, 5s2, 4d10, 1, 2, 3, 5. Is it 5? 1, 2, 3, 4, 5. 5p. Good? Easy peasy. All right? Just practice once or twice and you will see that it's really quite easy. You can take the longest one and can still fill things out. Okay? Because if you follow it through and you keep your numbers clear, and by the way, when you're counting the shell from the right hand side, okay, don't count from here, count from helium. Okay? Because otherwise this will keep you one short. All right? Gallium is not 3p, it's actually 4p. Got it? Okay. So count from helium, not from boron. Are we good? Yeah? Do you want to write it out again, or are we good? Okay. So that is your electronic configurations, okay, for just the normal elements. So we saw some patterns there, okay, you know the different blocks. Now let's talk about, let me just look at your chapter, okay? 1 second. So here's the Aufbau principle, periodic table, and then Hund's rule, Mendeleev, okay, so periodic properties. And I would like to do the ions also right now. I think they do the ions in chapter 9. I would want to do it now because we're right into it. So you might as well learn the electronic configuration of ions. So when you do the electronic configuration of ions, there are two kinds of ions, right? The positive and the negative one, the anion and the cation. So in cation, what happened? You lost electrons. Okay, in anions, you gained electrons. So you also remember, okay, from chapter 2, is that the elements that lose electrons are the metals, and elements that gain electrons are the non-metals, okay? So if you have to lose an electron here from group number 1, where is it coming out of? The last shell, okay? So here it is going to be the S1 electron. Here, S2 electrons, both of them. That's how you get the +2 here, okay? So that's the S1, S2. Here you're getting rid of the P electron now. But not only just P, you're also getting rid of the S electrons. So let's write for aluminum. And aluminum is 10. Aluminum ion, 3+. Okay, so you take 13 minus 3 electrons, so you have to fill out for 10 electrons now, okay? So 10 electrons, if you see, 10 electrons is actually neon, okay? And so you can look at neon also and fill that out, okay, if you want to, or you can just do the electrons, which is 1s2, 2s2, and then 2p6, okay? The most important thing in ions when you do this, for cations, is you get rid of the last electrons, not the first ones, okay? So you're not getting rid of the inner electrons, you're getting rid of the outer ones, okay? Now for the anions, let's say you have fluorine. Fluorine accepts 1 electron because it is -1. So again with fluorine what happens? It's 9 plus 1 electron, so that means you're filling out again for 10 electrons. Where does that extra electron go now? In the last shell, because that's the only place where there is space, okay, for it. So again, this is 1s2, 2s2, and then 2p6. Okay, so this is where the electron went. And for aluminum, the 3s2, 3p1. These 3 electrons were the one that were gone. Okay, that's not there anymore. And then here for anions, you fill in the last ones, okay, in there. Now, one term that is kind of an important one here, if you see aluminum, 10 electron, fluoride ion, also 10 electrons, and then neon is also 10 electrons, right? These are all the same number of electrons. These are called isoelectronic. Iso meaning the same, okay, same number of electrons. So these are isoelectronic species when they have the same number of electrons by the way of giving, taking, or not doing anything, okay? So that's one term that's kind of key. Now, with the transition metals, things are slightly different, okay? The main group elements are very straightforward, okay? We are very sure of that group 1 is going to give 1 electron, group 2 is going to give 2 electrons, and so on. But transition metals, if you remember, were fickle, right? Iron can be 2 plus or 3 plus, manganese can be 2 or plus, 4, 7, whatever. So where are those electrons coming from, okay? And technically speaking, when you fill out the electrons, which are the last shell electrons for transition metals?
D.
The last shell electrons. It's on the board also. The D are still there. 4, okay? The last shell is 4. What you fill in is a different thing, okay? You fill in D at the end, but technically, the last shell is this. So you will take those electrons out first, okay? Not the D electrons, okay? Because the D have gone to inside, okay? And so you fill out, you take out the S electrons first. So if you were writing for scandium, which is Sc2 plus, and so that is 21 minus 2 electrons, so you're writing 19 electrons, okay? With scandium is not 2 plus. Usually it is plus 1 or plus 3. So plus 3 is very easy, okay, because that's minus 3 electrons, and that is 18, and that is equivalent to argon, okay? So that is very, very easy. But if it was scandium plus 1, then let me write for plus 2. That might work out better. So 21 minus 2, that's 19 electrons. And so let's start with argon. I'll just do the short version. Argon, that is 18 electrons, and then I'm left with 1 electron to fill. So where does that 1 electron go? S or D? It will go into D then. The 2 electrons that came out, this is from 4s2. Okay, that's where it came out of. So then you have really 1 electron left in there. So take out the S electrons first because they are the outermost electrons. Okay. Couple other words for you which are kind of important in talking about location of electrons. So here's the nucleus. Here we have the shells, and n is equal to 1, n is equal to 2, n is equal to 3, 2, 8 electrons, and then 18 electrons. And you know that there are never 18 electrons because you fill out 2 and 6, and then you go outside, right? Technically speaking, so there's never really 18 electrons. You had a question there?
Yeah, on the last example, so 4s is the outermost shell.
Yes.
It still has less energy than 3D.
It still has the less energy, but it's outside. So it's easy to take electrons away from there. Yeah, that's what the thing is. Caitlin.
What about for the exception group, so like chromium and copper group?
You still take out the one from S first.
Can you please just do chromium 2 plus, just so I can see?
Just so that you can see it.
Just so I can see if I did it right or not.
Okay, all right, we'll do chromium 2 plus. And what's the number again for chromium?
It's
not
24.
2, I raised the 2. Okay, so 24, that means you're looking at 22 electrons, right?
Yes.
For chromium. All right, good then. So, do you want to just do the noble gases, okay?
I did the other one. It was 1s2, 2s2, 2p6, 3s2, 3p6, And then if I did it the way that you said to do it, where you take out the 4s
The S,
group,
uh-huh.
I got 3d5.
Perfect.
And that's correct?
That's correct.
So I just take out the 1 electron for the s group,
Yes.
and then I'm left with 3d5 instead of 4.
No.
It would be 3D4.
3d4.
Well, if you were to, oh yeah, right, my bad.
Well,
You're
good.
taking
I
out
guess
the
it's a
two
good thing we went
from-
over that.
You're taking out the 2 from the 4s.
You're taking out the 2 electrons from the 4s2 then.
Okay.
Yeah.
Even though
Okay. Yeah.
as
Okay, here is the rule of thumb, okay, for everybody, is no matter what, take out the 2 electrons from the S first, okay, no matter what. Whether you have exceptions or no exceptions, don't worry about that. If you have to write for transition metals, then take out the S2 electrons first, and then take out the rest from the rest of the D, okay, if you need to, whatever you need to. So take out the S first. Yes, George?
So in the chromium example, it was only 4s1, so we took away 1 from the S shell and then 1 from the D.
One from the D,
Uh,
yeah. Good.
That's what I was wondering.
Okay,
Sorry. Thank
right.
you. That's-
And in some cases, this is going to happen because there might be a question, okay, you know, this is this kind of an ion, where are the electrons coming from? Okay, in there. So that's when you have to actually specify the shells also. Okay, very good. So coming back to these electrons over here in these orbits, there are 2 kinds of electrons that we talk about in any kind of an atom. One are called the valence electrons, the other ones are called the core electrons, okay? Valence electrons are the outermost electrons. In the outermost shell, whatever the last one is. So that's what I was telling you about with the transition metals, is always get the outermost electrons, which is take out the valence electrons first. So valence electrons are the outermost electrons, and the rest of the electrons are called core electrons, and these are the inner shell electrons. And with the exception of the transition metals are a little bit different because you actually fill out the valence, the 4s2, and then you go to the core, right? Then you go inside, okay, to do the 3D. And then with F, it's even worse because you go really inside the core, okay, to fill those electrons out. So other than those, essentially all the chemistry that happens is actually in the valence shell. Okay, so when we talk about bonding in the next few chapters, we will be dealing a lot more with the valence electrons. Okay, and again, let me take you back to your lab, because there was one lab in which you had a question about valency. Okay, if you remember, what is the valency? What does valency of +1 means? What does the valency of +3 means? And that +1 and +3 meant these are the number of electrons you can give. Okay, that's what it really meant. So that's where the valence electrons come from, is the outermost electrons, and then this core would be inside here. Okay, so I have a question for you before I go through this and finish the chart here. At any given time, okay, and I'm going to stand over so you can't see a thing. At any given time, okay, for any of the elements in the outermost shell, how many electrons would you have at any given time? The maximum electrons you can have in the outermost shell. 8, then you stand by it. Good. Okay, anyone else? Anyone else? When you're filling out all of these electrons, okay, at any given time, the valence electrons, the maximum valence electrons possible are, there's only one number. Take a guess. Oh, 16. Stand by your answer, Samara. Don't think twice. Okay?
She's right, it's called an octet.
Hmm?
It's called an octet, she's right.
So she's right?
Yes.
Okay, so you have one person supporting you. Okay, anyone else? Anyone else? 2 zeros stacked on top of each other. How's that? That doesn't work. 8. 8 is the right answer. Okay, and I don't know what happened. What was the confusion? What are we thinking? Tell me what you're thinking, only then I can tell you.
Didn't we have something where?
And that's why I stood in front,
Yeah.
because right here is 8, 8, 8, 8, 8.
Oh, no,
The
but-
answer is right there.
When we were doing copper, we ended with 3D10.
But that is core electron, that's not the valence electron.
Because that goes
ended
back
with.
in, but it goes back in.
But it goes back in. That's what I was trying to tell with the
Oh,
valence
Jesus.
electrons.
Because when
So-
you get back here, you go back to 4.
So my question was about the valence electrons. So the maximum number of valence electrons possible are, everybody, 8, please, 8, okay? Because after you fill the 3p6 or 4p6, what do? You go to the next shell, okay? You start filling out the next shell. And then you go into the core with the D, and then you come out again, okay? So, and that's why I don't like this periodic table also, because it gives you the answers right there, okay? But you have to be close enough. I don't think, Max, that's close enough for you, okay? But anyhow, that's something that's, something to keep in mind when we get to the next chapter. How are we doing? Good? Okay, so that's a lot about electronic configurations. Now let me go through your worksheet and see if everything is done. Number 8, you can write SPDF notation. Do not use noble gas configuration. Okay. And then turn the page, question number 9 and 10. What is wrong? This is like my favorite question. Okay, what is wrong with something? And I think this is why I hated computer programming, is because I just felt like I was looking at everybody's mistakes, and so this is what this is also, okay, is looking at mistakes, okay, and here trying to see what is wrong and what is right. So here what you have to look at is very minute details, okay, and I will trick you, sorry, I'm very, very sorry, okay, but I will trick you with very small things like this. And that's bad. You really got to look carefully and then realize that you cannot have 3 electrons in the S. Okay, the maximum you can have is 2. Okay, or I will do this for you. Is that possible? Because you got to fill S first, right? Before you can start filling P. Okay, so those are the exceptions. So when you do these questions, I know you can figure out what is wrong. That's never going to be hard for you. I know that. The hard part is explaining what is wrong with it. Okay, so that's why I left some room here. So write for yourself as to what exactly is wrong with it. If you want to come back and check your answers with me, please do come by. Okay, and I will check for you whether your reasoning is correct or not. But you have to have a reason for why you think it's wrong. Be very specific in your answer, okay, when you're trying to do this. Okay, so that's your wonderful worksheet for electronic configuration. Now we go on to the second part of the chapter, which is periodicity. And this is not very long, it's kind of a short thing. And the other one is called diamagnetism. You probably will not get any specific questions as such for these 2 properties. But paramagnetism means that something can be magnetized. Diamagnetism means that something cannot be magnetized. Okay, so it has to do with the magnetic property. And how does that come around? Has to do with how you fill in the orbitals. Now, if you remember, was it Pauli's exclusion principles or Hund's rule or something, which says that you have to fill electrons singly first, okay, and then you start pairing up the electrons when you do the box configuration. So if you look at something like a half shell or a half orbital, okay, versus something that is completely filled up, okay, there's a difference between the 2. In this case, all of these electrons, they have an MS number of either -½ or +½ right? And let's say because it's going up, let's just randomly say it's +½ It could be negative also. It doesn't matter, okay? It's just the fact that they're actually facing in one direction. So if it's +½ all of these, then everything has a magnetic spin. It has not been nullified, okay? Whereas in this case, the MS number, you have the +½ but you also have the -½ right? Going in opposite directions. And because of that, the magnetic spin has been nullified. Okay, I won't say neutralized because it's plus and minus, but it's been nullified. So there's no north and south anymore. Okay, and so since we talked about magnetic spin number, which really is all about magnetism, okay, that's where this property is coming from. So any elements that have this kind of a single spin will also have magnetic properties, paramagnetic. okay? And if they don't have it themselves at room temperature or something like that, then you can make them magnetic as well, okay? And so some elements may not be magnetic at room temperature. You change the conditions, suddenly they do become magnetic, okay? And so it's a very important property. It's a very small feature of electronic configuration, but it's an important feature. And just today I was reading about how they make all these expensive items in the stores, how they make them proof, what do you call it? Stealing proof, like, you know, shoplifting proof. You've seen those little magnetic strip bars on them, and they go out and go beep, beep, beep. Yeah, that's a magnetic property, okay? And that's something that, you know, that happens when you pass through those two bars, and there's actually magnetism in there. And so there's a little thing in the strip also, which gets activated then, okay, when you pass those through that magnetic thing, all right? And so, yeah, it was kind of interesting. But anyhow, that's what the magnetic properties are, paramagnetism, diamagnetism. You can take something like this and also convert it into a magnet, provided that you give it enough energy that all the spins are going on the same side. Okay, so if you can make this into that, then also you can magnetize, but this is very hard to get. You know, so it's a tough thing. So this is what magnetism is. And eventually, if you go on to more chemistry classes, you're going to learn more about this feature later on. But it's one of those little things that I completely forgot, and you know, but it's there. Okay, page 315. That's where you find it.